So let's go ahead and talk about then this, or finish talking about this idea of systems. We looked at a cardio, we went to anatomy camp, a lot of us, right? Raise your hand if you went to anatomy camp with us. All right, so a lot of you, not everyone. Those of you that didn't, you may be invited to the second one. That's next week, Thursday. Your teachers and I are meeting tomorrow. Tomorrow during the after school. So, in anatomy camp and in our previous discussion, we looked at that system, that the circulatory system, right? It's a system, which means you have a component. You have this heart that's divided into 4 chambers. You had the blood vessels coming back from the lungs. You have the blood vessels coming from the rest of the body, from the top and the bottom. You had the blood vessels that took it to the heart. And let's go ahead and use that. Let's say blue. Took it to the heart, both sides of the heart, right? Or the lungs, 2 lungs. And then you had the blood vessels that came back from the lungs that brought it to back into the heart. Does that make sense? Right? Yes or no?
It makes sense with the illustration.
The illustration does not make sense. So you don't see that the blood is coming from the bottom of the body, from the top of the body, into the heart, into the atrium, right? Into the right atrium. Then from the right atrium goes to the right ventricle. From that right ventricle it goes to the 2 lungs, the right and the left lung. Picks up oxygen, the blood comes back from the 2 lungs, it's red now, right? And goes into the left atrium, then from the left atrium into the left ventricle, from the left ventricle then to the rest of the body, right? What are these? What are these little lines, all these crazy lines I'm drawing? Arteries and veins and arterioles and tiny little capillaries. And this is all a circulatory system, so it's all connected, right? We separate arteries and veins as if they're 2 different things, but it's actually all part of the same loop. It's called and let's be clear on this. Let's make it simple. Everybody agrees this looks complicated, right? So let's make it simple. That's what we like to do in science. I know people think that we're making things complicated, but really what we're doing is we're making really complicated things easy. So really what we have is a box. The box represents the heart. It's broken up into 4 chambers. You got big blood vessels that come in and out of the heart. They go to different places, right? That are defined, where they go and how they go are defined by their function, right? So the blood vessel that comes from the rest of the body has to go into the heart from the top and the bottom, and the blood vessels that go everywhere else to the body has to have some that go up to the top and some that go to the bottom, right? And then these have to come from the lungs. So that kind of stuff is easy. But then what you have to remember is that these things have to be closed. It has to be looped. They can't be open. They're not open, right? You're not a sack of blood. All the blood is inside the blood vessels. Does that make sense to everybody? So they're constantly in the blood vessels. These loops are continuous. They get connected. And they have to find their way to every part of the tissue. And when they get down to the very, very tiniest parts, they get real small. They become so that only one cell can fit through. They get so small that only one cell can fit through. And on the other end, they're connected. They're not. So right here, between the blue and the black here is where you see the vein versus the artery. But you see that the vein and the artery are the same they're connected as a tube. Does that make sense to you? That even though it is a closed system, even though we call this one, well, that shouldn't go that way. That's a bad connection. Even though it's a system, it goes into bigger and bigger veins and arteries, and that's not true either. These get connected to a big vein. That big vein is called the vena cava. Hold on. So the key is that you understand that this system, all these different veins, sort of like a creek or a river, they all kind of combine into bigger and bigger rivers until they finally flow into the ocean. Well, that's how your veins and arteries go, right? So they all go into this big vena cava, and there's one that comes from the top as well. And they feed right into the heart, all the blood vessels from all over your body. But look, it comes out of the heart, right? And goes into these things called capillaries. And at the capillaries, they exchange oxygen. I don't know what you're doing, but I'm in the middle class. If you can wait till later, it'd be great. Come back at the end of the period. So here at this point, one cell exchanges gases. And then as gases are exchanged, they move back up into the veins, it gets back into the heart, gets transported to the lungs, etc. But I guess as complicated as that seems, can you imagine how many thousands of blood vessels there are? How many different tissues? Because every part of you is alive. So every part of you needs oxygen. You have to take oxygen from the air that's in front of you that you can't see. You have to take it into your lungs, put it into your blood, and then transport it to every cell of your body. Those toes, the little toe at the bottom of your foot, needs oxygen, and it gets the oxygen from your lungs. So you have to have these blood vessels that take this oxygen all the way down that little toe. And that's complicated for us. But can you imagine how complicated it is for a giraffe? Or an elephant? It's the same system. So this closed system, this pump that pumps this blood around, can you imagine how many different components there are? How many different things can go wrong? How many different ways can this system break down? The more complicated the system, the more ways there are for something to break down. And it goes back to, what is a system? What is a system? There's a word I keep using over and over again, system. I would know that. That's going to be on the test. I'm telling you it's going to be on the test. There should be no surprise that it's going to be on the test. So what is a system? In this case, we're talking about anatomy, right? Anatomy has systems. But we can define a system in every way. We can define it in a very simple way. You've heard of star systems, haven't you? Star systems. So solar system, excellent. So in a solar system, what do you have? You have the sun, right? And you have planets that go around the sun. All right? So it's a solar system. So you have... Say what? I'm glad you find it looks like a cookie. I hope you remember that it is a system. And what is it? What makes it a system? Yeah.
Because it has many different components.
Beautifully said. That's right. It has many different components. Many different components, and each component can influence every other component. So if this planet is part of the system, and this planet, something hits it like a billiard ball, right? Like a pool ball, right? Just like in a game of pool. If something comes in from outer space, a comet or meteor, hits this thing and knocks it out of orbit, you would think, well, too bad for that planet, right? But it's not just that planet, right? Because what happens if that happens? Yeah.
It'll start, if it goes out of orbit, it'll go either into someone else's orbit
That's right. It's going to mess everything up. It doesn't just mess this planet up, it messes this planet's orbit up. And then maybe there's another planet over here and that one gets messed up. Maybe the sun gets impacted. I don't know. Maybe you mess up the orbit of the sun because the sun itself is orbiting in the galaxy, isn't it? Sometimes there's two suns orbiting each other. So there's all this stuff that happens that you have to really consider when you're looking at a system. A system is something that's more complex than just the simple version of life that you've been taught up to this point, right? That, okay, you breathe oxygen, that's it, yay. That's not that simple, is it? You have to take the oxygen in, you have to bind it. It has to be released at the right time. You can't just have oxygen just floating around in your blood. That's no good. It's called an air bubble and you die, right? So you have to have it attached to something. It has to be transported in a specific way. And it has to go and be released at the right time. You need to have enough oxygen left in your blood to release oxygen down at your little toe. Because that blood has to go through and flow through all your whole body and get down to your little toe and then come back up. If not, that little toe is going to turn black and die off and fall off. That's no good, right? Yeah. If it dies, your tissue dies, what happens to it? It rots. What happens? You've never seen a zombie movie? What happens to zombies? They lose their parts and pieces all over the place, right? Yeah.
So is that why if you hold your breath for long periods of time, then if you pass out, it's passing out because your body's trying to shut you down so you can start to move again?
You're passing out is because your brain needs oxygen. If your brain doesn't have oxygen, it doesn't work. If it doesn't work, you don't think. If you're not thinking, you pass out. That's what passing out means, is you stop thinking. Your body's trying to save the higher level thinking, this consciousness, this stuff that you call you, and that you recognize me, say, hi, how you doing? That part takes a lot of oxygen. So you have another part of you that keeps your heart beating, keeps the rest of your body alive. That part can keep going, and you still be unconscious. The first part that goes numb when you become unconscious is your thinking part, your conscious part, because your body prioritizes, right? It starts with the medulla oblongata, right? The part of your body of your brain stem, right? It's not your medulla oblongata, your brain stem, right? And your brain stem then controls what? Breathing, heartbeat. So your body wants to make sure that part is still working. Even if you don't recognize who you are, you don't know where you are, at least your brain's still, you're still breathing, right? So that gives you a chance, doesn't it? A fighting chance to come back. If you can't come back, that's okay. Some animal will find you and eat you. But you'll be someone's food. But that's fine, right? But if you do come back, that's your second chance. Good, you're up, you're awake, you're moving around. So that's what happens when you stop breathing, whether because you're drowning or someone's choking you or you just pass out because you hyperventilate, whatever the reason. When you pass out, that's what's happening. It's not you restarting, it's you trying to save whatever part of the brain you can save. Yeah.
So when I was younger, I got my ears pierced and it turns out I was allergic to nickel from it. And I passed out. And ever since then I pass out once a year or something like that. But I pass out a lot from it. And from my ears, I pass out. Why?
I'm not sure that it's your ears that are making you pass out. You have to talk to a doctor. I'm not a physician. I would tell you that it's highly. I can't imagine it's your ear just repeatedly throughout your whole lifetime making you pass out once a year. I don't think it's that simple. I think something else is going on. I don't know why. Low blood sugar, anemia. There's all kinds of reasons. Because again, what are we talking about? See, this is a good point. Is that this is a system. You are a system, and right now I only talked about one part of that system. You're part of an organism that has many systems. This is the cardiovascular system, but you also have the respiratory system, you have the endocrine system. There's a ton of systems that work together. Any one of those things, one little component, just like that planet, right? Any one little component can send one system into imbalance, which can then impact another system, which could then knock you out. So it's really difficult to say. That's why physicians get MDs, and you go and you see specialists, and you have all these different tests Because any one of those things can cause a disease. It's not as simple as, well, I pass out, so what is it? It's not that simple. Well, I don't feel good. What is it? I have cancer. What caused it? It's not as simple as all that. It's complicated. And so you have to start doing tests and say, okay, it can't be this because this is the result of this test, and it's probably not this, and it's probably not that. It looks like it's probably this, and let's go look at that and see if that's the cause. And how do you figure it out? You fix this, and if the symptom is repaired, then that was the cause. And you just keep doing that until you figure it out. It's like any mechanic does. What's a car? A system, right? And that's, if you know any mechanics, that's what mechanics do all the time. Well, geez, the car's making a noise. Well, what's causing the noise? I don't know. Let's test it. Let's turn this off, and let's take this out, and let's replace this and see if that works. And if that doesn't work, let's replace that. And if that, $3,000 later, you figured out what the problem was. Because it's not that simple. It's not, now some things you know. You know from experience, right? So I hear a noise every time what's it going to be? All right, my car doesn't start. My car doesn't start at all. It won't even turn over. It doesn't go, right? I turn the key and nothing happens. Well, it's a battery. Or it's an alternator. Because if it was anything else, I would hear something when I turn the key. Do you see how that works? You know how the car works, so then you can say when something goes wrong, it's probably this, let's start looking in this direction. That's what you're doing here. You're learning how the system works. The systems that we're talking about are life systems, so that you can diagnose future problems. That's how diagnosis works. Whether it be you're an ecologist or someone who studies ecology, or you're a doctor, you're looking at the human system, right? Or you're a veterinarian, you're looking at various animal systems, or you're a botanist and you're looking at plant systems. Whatever the issue is, you need to know the fundamentals. How does it normally work? So when something goes wrong, you can figure out what's wrong and how to fix it. Yeah.
Would you consider a pen as a system?
A what?
A pen.
A pen. Almost everything. So let's take a look at a system. One of the systems that you're going to be looking at this week, right? We're going to be doing some experiments this week. Let's take a look at a system. Watch this. I'm going to draw a really, here it is. It's a beaker with a liquid. See, you assumed it's water right away. That really bothers me. I wish you'd all would listen to me. Just because it's liquid does not mean it's water. It could be anything. It could be a lot. There's liquid metal. Depends how hot this is. There's liquid rock. We call it lava. Right? It could be any. You don't know what that is, but you think it's a liquid because it has this erratic surface. That's good. Okay, that's what I meant for you to think. I made it blue, so you automatically made that connection was water. I get it. By the way, water is not blue. It's clear. The ocean's blue, but that's because it's reflecting, right? And refracting. In any case, you have this beaker. This beaker is a system. What are its components? What is it made of? What does it? We don't know. We haven't told you, right? It could be salt in there. There could be all kinds of minerals. Of course, there's an interaction. It's open. This is called an open system, right? What does it mean to be open? What's an open system? That's a new vocabulary word right now, so let's think about it. Open system versus closed system. What's the difference? This is an open system. What does that mean to you? Anybody guess? Just guess. Yeah.
The open system is like something that's open at the top or open at all.
It's open at all, okay, but you're using the word that's in the word in the definition.
That's exposed to something.
Exposed. Good, I like that word, yeah. You were going to say, yeah? You were going to say the same thing? Yep, next.
Is it like exposure to air?
Mm-hmm. It could be exposure, in this case, exposed to air, good, yeah.
I was gonna say anything that has an outside
Outside interaction with anything on the outside, right? So something that's meant that you have a separation from something else that has that, but it still can exchange materials. Is that fair? All right. Can we say that? Can we say? Is that going to be okay, guys? If we say exposed, an open system. An open system is any set of components that work together and have interaction with other material or energy from outside Does that make sense? So an open system is anytime you have a group of components. So in this case, in the case that we're talking about here, it's a beaker, right? And in this beaker is this liquid. Now, someone already said it, but there's stuff can go in, right, from the outside. And what could also happen? Stuff can go out to the air. So a glass of water is an open system. It can lose, if you leave a glass of water on a table on a hot day, what's going to happen to that glass of water? It's going to evaporate. It's going to start off here, and then over some time, it'll end up down here, and then over some more time, it'll be dry. It'll be empty. Where'd all that water go? Went into the air, because it's an open system. It's exchanging material, right? It's exchanging components. The stuff that so that means that this stuff must be made of things, tiny little bits, right? Little components. We call them, you're taking Mr. Custer or Mr. Krishnan's class. What are these components? Yeah. Molecules. They're made of molecules. You've heard of this statement, yes? From Mr. Krishnan or Mr. Custer, you've learned that these are molecules. These molecules, you say no?
No, we don't have them.
You have who? So then you have Miss Bancor because you should know that they're called molecules, right? You should know they're called molecules. If you're taking Miss Bandicourt's class, right? That's why you were selected there, because you've taken physical science already. You know this. That's physical science. It's something that you're going to have to catch up on then, okay? So these little tiny things are called molecules, and they leave in an open system. They can leave. We call that, someone already said it, evaporation. When they're leaving, when it's leaving, right? When it's coming in, it's called condensation. So you should know those two words. So condensation is when anybody with glasses knows what condensation is, because when you have your glasses on, you go from hot to, you're just like, I can't see. Oh my God, you know.
You in the shower?
Oh yeah, you go in the shower, and if you leave your glasses on because it's in the morning, you're like, what just happened? I can't see anymore. Where's the soap? It's annoying. Those of us with glasses, we're brothers and sisters. Those of you that are without glasses, you don't understand anything. All right, so. Yeah, all that heat. That's also annoying. Yeah, and also anybody that drives that's in a car in the cold morning or in the winter time or in the humid day, you see how the window fogs up and your mom is sitting there trying to turn on the wipers and wipe the inside, and she's probably going, oh my God, I can't believe this is happening. I can't see. That's condensation. Where's that water coming from? It's coming from the air. The air is the water. There's molecules of water, and water has this. This is important because this is the molecule for all life on this planet. All life on this planet. This is arguably the most important molecule. It's called water, H2O. 2 hydrogens and an oxygen with 4 extra electrons kind of hanging out on the outside of oxygen. Those of you that are taking conceptual physics, you'll go into a little bit of this. We'll learn more about it later in chemistry, but these are called electrons, and they're in the outermost shell or valence shell of an atom. And they share, and you've heard this before, valence electrons, and there's 4 of them sitting on the outside of oxygen that are extra, 2 pairs. And these lines represent, when you see a line, they represent electrons, shared electrons. It's called a covalent bond. You're going to need to learn that very quickly. These covalent bonds then are shared, they're held together. This is when you are sharing covalent bonds with atoms, we call this a molecule. This is what a molecule is. When more than 1 or more, actually 2 or more atoms are held together by a covalent bond, it's called a molecule. You need to know that. Yeah. 2 or more atoms held together by covalent bonds. What are covalent bonds? Anybody? That's right. Which means they share electrons. How that works and all that you'll cover in conceptual physics, or you should have covered it in 8th grade. So sharing electrons, I wish I had the time to sit down and spend a month. What I used to do this first month of school is go through this stuff with kids. And kids gave me the feedback, it was overwhelming. So that's why we instituted conceptual physics, and why some of you who've shown aptitude and shown that you've been already more, if you're having issues with this, you need to speak up to your teacher and have that conversation with them. So anyways, covalent bonds share electrons. This is when you have this system this sharing of electrons, we call this a molecule. The most important molecule on this planet, the most important molecule on any planet for life as we know it, is what? Water. And people from Lebanon and Palestine and people from Southern California, you know this. Why do you all know this more than anybody?
The water is very limited.
Very limited, because it's desert. Because Southern California is a desert. Because Nevada, New Mexico, Palestine, Lebanon, all these places are in deserts. Mexico, at least northern Mexico. We're talking desert, so water is very limited. The most important molecule on the planet is right here for life, as far as life is concerned. So, in any case, these are called covalent bonds. This water is a component. In this case, in this example, a component of this system. That system was a glass of water. You think of it as a glass of water. Is it pure water? No, it's not. It is not pure water. Even purified, quote unquote, purified water, filtered water is not pure. Water that you drink, spring water is certainly not pure. In fact, by definition, it has a lot of minerals in it. It has calcium and nickel and iron, and it has a lot of minerals in it. And you can tell that if you ever let water splash on something and then walk away. Tap water, splash on anything, walk away. When the water dries, if you let water splash on something in the sink, you're going to see lines. You're going to see like kind of almost a drip mark. The water's gone. What's the drip mark? What is that? What are these things that are left up on your sink in your bathtub, or that ring, right? You see, it's no. Actually, you would think it would be dirt from your body, right? But there are some oils in there probably from the soap and from your skin. But mostly, actually, it's not dirt. What do you think it is? Yeah.
Just different minerals.
The minerals, because what you have is you have a system. The system is the water. So I'm going to draw the water in blue, if you don't mind. You have the water. And then you have some other stuff, and we'll put some stuff in green. Maybe the green is some mineral. I don't care what it is. It could be anything. The red could be iron. The green could be nickel. Whatever. Copper. Maybe the green is copper. Whatever it is, there's probably tons of different minerals in tap water. Chlorine, what have you. Well, water, guess what? Water evaporates at about 100 degrees Celsius, 214 degrees. It boils. But water evaporates, its boiling point is actually kind of special. But these minerals, so water boils at 100 degrees Celsius. Iron is in the thousands of degrees Celsius. Thousands. All right. It's you're not going to get, by the time you get to the point where iron evaporates, turns into liquid and then into gas, it's going to turn into a gas. It boils at a lot. It turns into liquid in the thousands. It turns into a gas in the, I don't even know what temperature it takes to turn iron into a gas. But, so think about it, these minerals then, by the time they would evaporate and go into the air, how hot, do you think you'll have any water left? No, there will be no water left. All the water's already in the air. So the water leaves first. As the water leaves, what's left over is the minerals. And that's why you have those white streaks and white, we call them evaporites. The things left over after water evaporates. Because water evaporates at 100 degrees, but these minerals evaporate at thousands of degrees. So they're going to be around for quite some time. All right, so that's kind of what a system is. And of course, we're going to be looking, there's another system you should be aware of. It's a cool little system, actually. One of my favorite systems, and probably the most important system as far as we're concerned. Right? I guess you could think of it as a car. You might. Yeah, the Earth.
Okay.
Oh.
Okay. Oh, wow.
Whatever, man. You know what I should do? What I keep thinking to myself, what I should do is get all these kids that have such big mouths to come up here and do it, and see what happens. It does kind of look like it's meant to look like it, but I'm not an artist, so I'm kind of sketching it. This is called sketching, and those of you that take all day to draw things and are like, wait a minute, I need more time to do this. Well, you don't have time. It's a sketch. That's why it's called a sketch. Do it. Deal with it. All right. So this is a system. This is a system. The Earth is called a what? What would the Earth be called? It's a sphere. It's not round. Somebody might say, hey, look, it's a little bumpy. It's not perfectly round. The Earth is not round. It's never been round. It's more of an ellipse, first of all. Secondly, it's not really even that. It's bumpy. It's very bumpy. We call those bumps mountains and hills, right? So it's not round at all. And there's actually a bulge at the equator because of the way the ocean actually bulges because of the moon and its pull on the Earth. But in any case, irrelevant. The point is, you got this system. We call it Earth. This system is called Earth. Is it an open or closed system? You would think, but actually there's very little exchange. That's right, it is kind of closed. It's not perfectly closed, obviously, and you know that, right? Because we get energy from the outside, right? We get something called the sun. So very far away, it gives us energy. So energy does go in, and energy does come out. So energy goes in, energy does come out. That's true. And also, what else goes in? We do have some materials go in. How do we... in fact, they just happened. The Perseid mispronouncing it, but the Perseid meteor shower just happened. So how did things come in? Meteors. They come flying in through the atmosphere. They kind of they catch on fire, and at least the outside as they come in. They hit the ground. Some hit the ground, but most of them evaporate. They get burned up in the atmosphere. But those atoms, those molecules become part of our atmosphere, and they'll settle down when it rains over time. So that material is coming from outside our system. Don't put stuff away until I dismiss you. So. Also, comets, energy, we have some matter going in. Some matter goes out in the form, in fact, we're losing most of our helium because some of the atmosphere, right, does go out. It's very little compared to how much we have. But some atmosphere goes out. Something comes along and swoops it out. Hopefully not a lot of it because we need it. But helium easily gets lost, goes into space. In fact, we're probably going to run out of helium because that keeps going out all the time because it's so small. It's not held to the earth very strongly. It doesn't really react with anything else, so it doesn't get stuck in the earth very well. So yes, bless you. So it goes off into space often. But for the most part, the system's closed. So you can have a system that's kind of depending on what part of the system you're looking at. For instance, water's pretty closed. Water stays on Earth. It has been around. The water you're drinking now, dinosaurs peed it out millions of years ago. Right? It's been here. It's not like we're making new water every day. We don't need to make new water. It gets recycled. Oxygen. The oxygen you're breathing in, dinosaurs, ancient plants broke it off from water all the time. Plants break water up and we put them back together all the time. So a closed system means that you don't have material. It's the opposite of an open system, right? So if an open system is any set of components that work together and have interaction and do have interaction with other material or energy from outside, a closed system what? Doesn't. Yeah.
Is there such thing as a semi-open system?
Yeah, it is. That's what the Earth is. Most things are, right? It's very hard to have a truly closed system, right? It's really hard to have absolutely no interaction. If we sealed this room and just had a window, would we really have a truly closed system? No, because what would happen through the window? Light would get in. And so light's going out too. Could we have a completely closed system? I guess, sort of, yes, but it's hard. It's not naturally closed. It's hard. It would be hard to have a complete, it's not hard, but the systems that we're going to be worried about in biology are semi-closed, if you want to look at it that way. Right? Even you, are you a closed system? You're kind of hard depending on what you're looking at. It's kind of semi-closed. But of course you're exchanging oxygen, right, and carbon dioxide, so that's leaving and coming, stuff's coming and going, right? And you're eating, that stuff's going in, and you're pooping, that stuff's going out. You're peeing. Actually, the pee is what comes out of you. Poop doesn't actually come out of you. Poop is what's left over. Did you know that? That poop does not come out of your body. It was never in your body. You think there's bacteria in your body? You think there's these bacteria eat us. Why would we let them into our body? And poop is 60% of your poop is bacteria. That doesn't make sense. Poop is the inside of your stomach, the inside of your intestines, actually still on the outside. Did you know that? Yeah.
When you die, someone they measured the amount of bacteria and
Let's go ahead and do it. So one of the things about systems, and again, a system is, see who's done their homework. A system is what? Yeah, go ahead.
Is it any set of components that work together?
Any set of components that work together, yeah.
When it has many different components and each component can influence each other.
That's right, when the components influence each other. And so you have a bunch of different little pieces and parts. Everything is impacting everything. And we talked about like a solar system as an example. And we looked at Earth as a system, we looked at human beings, right? We looked at the cardiovascular system. So there's all these systems, there are all these different components that each are working together to complete a function. And I want to emphasize that it's not necessarily a function that some intelligence has designed, like in a clock, right? Where we design a function as a bunch of gears and each gear is meant to do something. It could certainly be that. That is certainly a system, but it could also be just something, that it's not necessary. So it's, in other words, I'm trying to say that I'm not pushing any kind of agenda here. It is just take it with what you want as far as how it got there, but a system is a bunch of components that all work together. Negative feedback does the opposite of the stimulus, where positive feedback does more of that stimulus, encourages more of that stimulus to occur. And what do I mean by that? Well, let's take a look at something. Yeah.
What's stimulus?
Well, stimulus is anything that causes, right, something to happen. So let's say I walk behind you and I poke you with a sharp object, right? What's going to happen is you're probably going to scream and probably punch me in the face, right? And at that point, I just stimulated that, didn't I? The sharp object in the sharp object was the stimulus for that reaction. So stimulus is the cause or the event that comes before what you're looking at. So let's take a look first at this idea of, sorry, I have all these pre-written things out here I'd rather not get rid of, but homeostasis. Homeostasis is, and you need to know this word, it's an important word, it will be on the test, along with stimulus, along with negative and positive feedback, along with system. These vocabulary words will be used in context, and you'll have to solve problems for the next test, and the next test is going to be next week. So homeostasis is keeping the system at a set point. So when you have a system that's kept at a set point, so by homeo means same, all right, and stasis means still, doesn't move. So when set means that you're not going to change it, right? So that point is not going to change. Where homeo and stasis means not change, where homeo means the same. So it's a stable set point, whatever that is. You'll understand better when we look at the example. Equilibrium is this idea, and who's taking conceptual physics? Anyone in this room? I think most, or is there a couple of you? So you've covered already a little bit of the covalent bonding and atoms, and you're probably just starting chemical reactions. Is that right? So in any chemical reaction, there's an equilibrium. And equilibrium does not mean that both sides, you have this equal number of product and reactants. What equilibrium means is you have the movement in one direction equals movement in the other direction. That's what equilibrium means. That movement in one direction equals the movement in another direction, the opposite direction. Because there's still movement, in other words, because you're still moving, it's just that the movement is equal in both directions, we call it dynamic. Dynamic means it's moving. Static means it's still. So those are words that I have not written down that hopefully you've written down yourselves. That dynamic means moving or changing. Yeah. Where static means, or stasis or static, or stasis means still. So if you're static, you're still. If you're dynamic, you're moving around. Does that make sense? All right. So equilibrium is a dynamic situation. In other words, that yes, you'll have the two sides, the movement in one direction is equal to movement in the other direction, but because there's moving, It's moving, it's dynamic. Are we good with this? Everybody okay? With so far understanding what I'm saying, not necessarily understanding the meaning of it, because we're about to look at some examples and try to understand what this all means. Yeah?
Can I see what stimulus is one more time?
Stimulus is the cause of something. When something's a stimulus, when something stimulates you, it causes something, right? Is that fair? Is that an understanding that everybody's okay with? So if the economy is doing bad and I'm putting together a stimulus package, what am I trying to do?
Cause it to get better.
To cause it to get better. That's right.
Can I see the positive feedback?
In a minute. We're going to go back over in a minute.
I got a question.
Yeah?
Is equilibrium in science have the same meaning of equilibrium in medicine?
In medicine? Medicine is science. But it's a field of science, right? It's not religion, it's not government. At least it shouldn't be. Medicine is involved in government when it comes to developing governmental regulations and governmental policies. But medicine itself is a science. And so equilibrium means the same, but in what sense have you heard it in medicine?
Oh, because, like, they say that, well, I heard it about a dog. My dog's equilibrium was off or something like that. And
Yeah, that's right. They're using it in the same way. And we'll talk about what that means. And what they really mean is that the homeostasis is not. And they could have meant equilibrium as far as their balance, right? Because if your equilibrium's off, you might not be able to tell which side's up and down. You get a little dizzy and you might fall. And so I don't know if that's what they're talking about. That's one sense of the word equilibrium. Still the same idea. It's dynamic. Their movement in one direction equals movement in the other direction. It's still the same kind of concept. Change in one direction equals a change in the other direction. Yeah.
So equilibrium is sort of like vertigo?
Lack of equilibrium would be vertigo, right? So equilibrium is when it's complicated, but equilibrium is established in the human body through the vestibular system inside your ear, in the inner ear. And it's a movement of liquids due to the gravitational pull. And there's these little crystals in that fluid that move. And as they move, they stimulate nerve impulses to your brain that let you know if you're looking up or down. So vertigo can involve a problem with the inner ear. So again, it's complicated, and I'd rather not get into it right now because that's not the intent here, okay? So in any case, so equilibrium is that balance. And so yes, you have balance, and if you lose that balance, right, that you end up falling, right? And a great example of the kind of equilibrium that I like is a seesaw. Everyone here has worked on it, has at least seen a seesaw. And if you put some bigger guy here and a littler guy over here, the bigger guy is going to, notice he's still not touching the ground, right? She's still not touching the ground. Neither one's touching the ground, but they're not really moving, but you'll see that but they'll, in this case, they're not balanced. No, they're not, it's not a horizontal, right? It's not like this. This side's heavier than this side, right? But they're also not moving, right? They've equaled. They're equal. So the difference is with dynamic equilibrium, that would be just equilibrium. Dynamic equilibrium, you're talking about there's going to be movement in both directions, and just that the movement in both directions is equal. So let's just go with that for now, and we'll come back to it in a little bit. And we'll see it again when we talk about osmosis and diffusion. So everyone here knows you have a thermostat in the house? Is everyone in here? Please, if you haven't, say something. You've seen your thermostat in your house? You know, there's your mom or dad are cold. They go over to the wall and they they turn a dial or they set a digital one. Yeah, you can press them. Some of them are pressed. Some even have your iPhone controls them or your Droid controls them. Oh, cool. Yeah. All right. So, but you understand that there's a box somewhere in your house that has that? Have you seen that? Okay. As long as we're all clear, because if this example doesn't work if you haven't seen it, or at least know that it exists. We have one right here underneath my hat. It doesn't really do anything, but at home, yours does control the temperature. So you have like 3 switches usually, and whether it's digital or analog means it's not digital, you're turning a dial or pushing a button, right? With digital, you're generally pushing buttons or moving sliders or something. So you have 3 buttons, it's either auto or manual, and there's another one that says heat, right? Or cold, or off. Because if it's a summer, you're gonna have the air conditioning on or off. If it's the winter, you're gonna have the furnace on or off. Does that make sense? Now here you have, there's 2 dials in a thermometer, in the thermostat. You have the set point. That's the blue one. So you set that to something. A lot of people like to set it to 70 degrees. Maybe you set it to 63. Maybe you set it to 80. I don't know, whatever. Whatever you're just going to set it to something. The other little measuring device, whether it be digital or a little needle, is the actual thermometer. And it's going to move. As it gets hotter, it moves up. As it gets colder, it moves down. So there's usually like, this is 90 and this is 40, moves in between that depending how cold or hot it is in the house. Does that make sense? And really good thermostats, they'll have sensors all over the house, in every room. So and they'll give you like the average, or they'll control the air handlers in every room. It's kind of crazy. They can get expensive, the HVAC system. So anyways, the thermometer goes up, and let's say it's the summertime, right? So it's getting hot. Let's say it's 93 degrees outside, and you're in a brick house, like in my house. And it's getting hotter and hotter, and it gets up to 90. What's happening to the air conditioner as soon as it goes above 70, above your set point? Because it's on auto. Once it goes up above 70, what's going to happen? It's going to go up. It's above 70. What happens? What is this going to stimulate? Turn on the air conditioner. And that's right. It's going to turn on the air conditioner. As soon as this thermometer goes over 70, higher than 70, the air conditioner is turned on. It stimulates, right? And it's based on a set point that you set. Is that clear? So now the air conditioner's on. What's happening?
Cooling off the house.
It cools off the house, and what happens to the thermometer?
It goes back down.
It goes back down. And now it crosses a set point again.
Then it's gonna go.
What's going to happen?
It's gonna go off.
The air turns off, and the sun's still shining. What happens to the temperature?
It goes back.
It goes back up. And then what happens as soon as it gets above 70 again?
Goes back down.
It turns on again, and what happens? Air gets cool, goes back down. And then it's beyond 70, what happens?
Same thing.
It turns off and starts warming up. It keeps doing that, doesn't it? Is it still? Is it not moving? No, it's moving. It's constantly moving. But it's constantly moving in order to do what?
To keep it at
To keep it around the set point, to keep it at the set point of 70. So it's moving, dynamic, to keep equilibrium, keep it at the same point. Equilibrium means equal, right? Keeping it all equal. In order to keep it equal at 70 degrees, it has to keep going up or down. That is dynamic equilibrium. That is homeostasis. We call it homeostasis. You do that in your body. What's your set point? 90? 97, different ones, yeah, 97.3, everybody has their own really, but 97, and that set point can change. I mean, if you're working out, it's gonna go up, whatever. But 90, let's just say 98.5, 97.3, whatever, okay? You have a set point. What happens if you go above your set point? You start sweating, and what happens to you as you start sweating?
Release stress hormones in water.
Huh?
That was the most serious.
I don't know what he's saying, but someone help me.
That's sweat.
All right, so what happens is you start to sweat. You start to sweat because it's hot, right? And what happens to your temperature? Well, the stimulus is the temperature increases, and then you start to sweat. But then what's the result?
It goes down.
The temperature goes down. Your temperature, and it'll keep going down. If it keeps going, if it gets too cold, then what happens is sweat. It stops, and you get warmed up again. So you're constantly adjusting your temperature. The other thing that could happen is if you get too cold before hypothermia, someone said hypothermia, but before hypothermia, which is true, if you get way too cold, you get hypothermia, that's a bad thing, you'll die if you're in hypothermia for too long. So before you get hypothermia, and everybody that's worked out, that's come into air conditioning in the summer, you're sweaty, you're wet from all the sweat, you've been playing basketball, whatever, you come into the house, it's air conditioning, what happens? You get real cold real fast, and what does your body start to do? And how does it do that? You know this. What happens when you get too cold?
Oh, the bumps is like all the chills.
Chill bump?
You get the chill. You get with the chill bumps. Your skin gets a little bumpy, like a chicken skin. And then what happens? So what else happens? Come on, guys. You shiver.
Oh.
Your muscles start to twitch. What is that doing when you're twitching?
Moving.
You're moving, and what does that do? What does that create? Heat. Your body's trying to create heat. It needs to because it's too cold. And so your body's doing what your thermostat in the house does. It goes back and forth all the time. Your body's always doing this. If it's too cold, you'll sit there. I can sit there and watch you guys. Oh. And you start to shiver. If you're outside and it gets too hot, you'll sweat. If you're not sweating and you're too hot, there's something wrong with you. You could die. Yeah, it is a real thing. Overheating. In the Army I actually went into heat exhaustion. And that's the first sign is heat exhaustion. And first you get heat cramps, then you get heat exhaustion, and then you could actually have a heat stroke. So it's really not a good thing. Yeah.
I was saying, how come sometimes you shiver even when you're not cold?
There are other stimuli for shivering, but in general it's because you're cold. And you might feel cold when you're not really cold. That's called a fever. So that's why your body gets hotter than it should, is because your body, you have a reaction to a bug, some kind of virus or some kind of bacteria, and your body's like, it's cold. Your body lies to itself and says it's cold. And so you start to shiver, so you feel cold. You could be 105, but you're feeling cold. And then that's what we call a fever. That's how your body warms up above its set point. All your body's doing is resetting the set point. And what it's doing is it's trying to kill the bacteria, because your cells are bigger and stronger, and your cells can take a little more heat than the bacteria can. So if they can increase the heat enough, the cells that are infected by viruses, or the bacterial cells in your body die quicker than your healthy cells. And so that in that way your body's able to fight viruses and bacteria. In one way, that's one way it does that. It's called an immune response. So there's two kinds of feedback that help what we just looked at, right? What you just looked at was negative feedback. In other words, let's look at what negative feedback is again. Remember what it is. Negative feedback is when you do the opposite of the stimulus. So the stimulus is getting hotter. What does your air conditioning system do at home if it gets hotter? It turns on, cools it down. So when it gets hotter, the system cools it down. That's called what? Negative feedback, because you're doing the opposite. Is that clear? When you're outside and you're getting hot and you sweat, that does what? Cools you down. And so what do we call that? Negative feedback, because it's the opposite. You're doing the opposite of what you see of the stimulus. So now positive feedback is when you do more of the same. As you get hotter, it gets hotter. As it gets hotter, you get hotter. and you just keep getting hotter and hotter and hotter. Now that's no good. That breaks homeostasis, doesn't it? That upsets equilibrium. So you have to understand that one, the negative feedback actually supports equilibrium, and the positive feedback actually upsets equilibrium. Now, negative and positive feedback, I can tell you that it's different from what you might be used to in an English classroom, let's say. Somebody gives you positive feedback, it's like, oh, you're doing a great job. And somebody gives you negative feedback, it's like, that wasn't so good, right? That's not what we're talking about here. We're talking about a loop, a mechanism, a system that's reacting to stimulus. So you have a stimulus, and if the stimulus is opposite the reaction, the consequence, the stimulus stimulates something that's opposite, we call it negative. If the stimulus stimulates something that's in the same direction, we call it positive. And negative feedback helps keep that set point. Just like that thermometer example, try to remember it. Well, one really great example that you've already covered, assuming you've done your work, we've already covered it, because you've read that sunflower case study, right, about global climate change. So as the temperature of the Earth increases, what happens is you increase the concentration of CO2. As you increase the concentration of CO2, what happens? Increase temperature. As you increase temperature, you do what? Increase CO2, and you increase methane release, and you increase other global climate change gases, and as you keep increasing those, what would you call that? I mean, it's global warming. It's positive feedback. So as you increase the CO2, you increase the temperature. As you increase the temperature, you increase the CO2 release, and therefore, you have a positive feedback loop. In other words, it's just going to keep getting worse and worse and worse and worse. It's hotter and hotter and hotter and hotter. It's never going to regulate around a set point. Does that make sense? You're not... Negative feedback would be something that's opposite that, where you can, as you go too far in one direction, the feedback mechanism brings it back down. This is a really important example in nature. We find it everywhere in nature. It's in your body, all over your body. In every part of your body, you have these feedback mechanisms. Some are positive, but very few. Most of them are negative, and the reason they're negative is because it helps keep it around a set point. Very important in your body. Think about it. What's the pH of your blood? Around 7. Why? Because you need to have it around 7. We'll talk about what happens to proteins when you go above or below that. But you need to have everything in your body. You ever go to a doctor's office and they take blood?
Yeah.
Have you ever you've never had anyone, have you gone with your parents or grandparents and they've taken blood? Yeah, they'll take it out of your finger, they'll take it out of your vein, they'll take a sample of blood to test it, right? Has anyone ever gone and peed in a cup, or gone with their parents and peed in a cup, right? What are they testing? When they test, what are they testing for? When your numbers, pH is 1, it could be ion concentration, it could be a lot of things. What are they really testing for, though? On a very, very fundamental basis, what are they testing for? Yeah.
To see if anything's wrong with it.
How do they tell if something's wrong?
Negative or positive feedback?
Negative feedback is what keeps it right. But how do they tell if something's wrong? Yeah.
They get a
I like how you're thinking, Antonio. You're like, we've been talking about negative and positive feedback. It has to be one of those two. Yeah, but yeah, no, it's good. I'm complimenting you. It's good thinking. But no, that's not. But think a little deeper. Yeah.
get a positive and negative control group.
I love your thinking. That's right. You're kind of connecting it to the positive control group and negative control group. Absolutely, you're right. That is how you do it. You're going to compare it to control groups. But what is it that they're testing for that you're not what? If they're testing for salt, they want to know what? If they get a number, you got a number, they're going to compare it to positive and negative control. Very good. That's excellent thinking. You're right, they're going to look for negative feedback mechanisms that make sure they're working. But you got a number, let's say it's 12 milligrams per liter, or 12 micrograms per liter, whatever it is. What are they worried about? Yeah.
Don't they want to see if there's like any drugs or alcohol in it?
Yeah, they could. That is one possible test. So you got this number, 120 micrograms per liter. What is that? They are going to compare it to something, a positive and negative control. That's right. But what are they going to look for? If it's, what does that tell them? How do they know that negative feedback loops are actually working or that you're sick? How do they know if you got 120 micrograms per liter? A set point. Excellent.
Good job.
Excellent job. I was worried you guys were not going to get that. Whew, that's a relief. So 120 micrograms, there's a set point. You have a number that it should be at, right? That's right. So you can't tell. Your positive and negative control group are going to tell you if it's what's too low and what's too high. And your negative feedback loops are going to keep it around that set point. So maybe your set point's 66 micrograms per liter. If you got 120, what are you worried about?
It's too high.
It's too high. And generally they give you a range. They don't tell you a number because everybody's a little different. They'll say, well, your negative control is if it's too low, we're going to say 30 micrograms per liter. And if it's above 110 micrograms per liter, then we're going to say it's too high, right? And so what you end up with is a range. And if you're in this range, it'll be green, and you can see it. You'll get a little green bar. You're good. And if you're outside this range, ooh, that's bad, or that's bad. All right. That's all medical numbers. You go to look at your parents' numbers. Almost all of them, they're looking at some range, and there's some set point, and you got your value, and then you compare it to too low or too high. And you look at to make sure that you're within some kind of set point, set range. We call this a range. Is that good for everybody? So we call it a range because somewhere within here you're okay, you're good. Now that's true for cholesterol number, right? HDL and LDL, you've heard of these things?
No.
Well, there's high density lipids and low density lipids. Those are two forms of cholesterol in your blood. You're too young probably to worry about it. Your parents probably are very aware of it. Oh, good. Yeah, that's an excellent source for us. That's right. Some of your parents might work in hospitals. They'll drop. Excellent. And so you got the other thing you might have heard is blood pressure. Who knows what a normal blood pressure might be?
Isn't it like 90 over something?
Okay, well, I should say normal blood pressure changes depending on a lot of stuff. Like, for instance, if you're working out, then you expect your blood pressure is going to be higher. Does that make sense? And if you're stressed out, then you kind of, you expect that there's someone's blood pressure. So you go in and somebody measures 160 over 90. You're not going to freak out. Because maybe you just came up a bunch of stairs. Or maybe you just found out your dog just died. Or maybe you're stressed because a test is coming up. Or you know what I'm saying? There are stresses that you expect blood pressure to increase because your heart's pumping faster. If your heart is pumping faster, you could be in love, and that's going to increase your blood pressure. That's going to turn your face red. That's why people blush. Because they're getting emotional. When you get emotional, your heart pumps. That's reasonable. So blood pressure is something that can change depending, and a lot of your numbers can change based on a bunch of different reasons. But normal blood pressure, right? Yeah, they give you kind of a range, but normally you want to look for 120 over 80. So there's two numbers, diastolic and systolic, and if you get 120 over 80 to about 140 over 90. And you're not exercising, you're not, somebody didn't just die, you didn't just come up some stairs, then you're anywhere within that, you're within tolerable. You go in and somebody takes a 250 over 100, what are you thinking? Oh Lord, something's going on. It could be acute, it could be high blood pressure that moment, or they could have chronic high blood pressure, which is really bad because it does a lot of damage to your body. Okay, yeah.
I know that in my family, most people have about a 90 over 70, I believe. But then, our family tree is like my grandpa, my dad, and then we all have like 104 over 80. So it's like higher than the rest of our family.
Well, I'll tell you this. There are people with low blood pressure, and low blood pressure can cause some issues. All right, so it is something to be concerned with. But low blood pressure, generally you're talking about like 90, right? 90 over 60, 90 over 50. If you get 80 over 50, now you're starting to get into dangerous low blood pressure. Because low blood pressure will make you faint. Low blood pressure gave my mother strokes, right? So you can actually get strokes from blood pressure is too high or too low. So but too low. What's too low? You know what? Talk to your doctor. That's why you pay them money, because they know what they're talking about, right? All right, so you go through these numbers, and every time you're looking at these numbers, what are you talking about? You're talking about set points. You're talking about homeostasis, because your body's constantly trying to keep homeostasis. And it's dynamic equilibrium. And the thermometer is a classic example, and that thermometer example happens in nature all over the place. So, all right. So let's go through this. This is the Earth's energy budget, and we're looking at the solar radiation coming in. 100% of the solar radiation coming in. About 22.9 of those 100 units are absorbed by the atmosphere. Now that's important because you have to think about the idea that that energy is there, and that energy causes motion and causes things like wind and increased temperatures, which then can cause increased evaporation, et cetera, et cetera. It can cause, well, we'll talk more about what the cause is in a second when we look at the actual molecules themselves. So once you get rid of that 22.9%, remember we lost 23.2% of that shortwave radiation. Does anybody know what shortwave radiation is?
No.
Has anybody ever covered that in middle school?
No.
All right, so what is shortwave radiation? What is longwave radiation? What is this wave business about? Well, it turns out that you can have, when we look at waves, we can draw this thing that looks like this. Have you seen this before?
Yes.
It looks like a wave because it is. It's like an ocean wave. That's where you get this ocean wave idea. And when we measure the length of the wave, we can measure it from crest to crest. This is a crest. A crest means at the top of the wave. So we can look at the top of the wave, and we can measure from one end to the other, and we call that a wavelength. That's the symbol for wavelength. Now, some waves are longer than others. So we have this wave that looks like that, and you look at another wave on the same axes, and we can see that another wave can be much longer. Do you agree that this wave, wave 2, is longer than wave 1? Do you agree that it's longer? All right, so the difference in their lengths turns out to impact how they act and interact. So here they have these two waves, wave 1 and wave 2. Wave 2 is longer. And it turns out they have more intensity as well. The waves that you don't really, the waves that you think of when you think about waves, you think about things like ocean waves, right? Some people might think about sound waves because those are actually waves. The same kinds of waves that happen in water also happen in air, because water and air are both fluids. You can pour air, just like you can pour water. That's what makes it fluid, right? Yeah.
That's cool.
So, in fact, the flowing of air, you call it wind, right? So it turns out that air moves very much like water. So the more, yeah, just mute it or turn it off, please. And so there's another kind of wave that actually acts very much like the water waves or air waves in many ways that you really don't think about. We call it electromagnetic. Anybody know what another word for electromagnetic is? All right, so this electromagnetic energy comes in various wavelengths. Now, the visible wavelength, the light we see. Do anybody know what colors of light we see? Anybody?
Yellow, white.
Here it is.
Oh, the rainbow.
Red, orange, yellow, green, blue, indigo, and violet. The rainbow. So this is now when you get on this side of red, before red, below red, we call it infrared. And that goes, infrared light ranges anywhere from something like 1,000 nanometers, to, you know what, we did scientific notation, didn't we?
Yes.
So Roy G. Bibb, the colors of the light spectrum, the visible light, the stuff we see, right, is in between 10 to the negative 6 and 10 to the negative. Let me put a range.
You didn't put the negative in.
I did. It didn't come out for some reason. 10 to the negative 6 and 10 between 10 to the negative 6 and 10 to the negative 8. All right. And between somewhere around 10 to the negative 4 it's bigger, right, because it's a smaller negative, is infrared. And now infrared, inside this infrared range, you call this stuff this. What is it?
Household.
It's too small for you to read, so let me. What you call this is this. Heat, that's right. So heat, what you know is heat is inside the infrared range. It's 10 to the negative 4. So where the wavelengths of light are 10 to the negative 4. The wavelengths of light, as they get bigger, they get 10 to the negative 2. Now we're talking about stuff that you might have heard of. It's radar. Radar waves are 10 to the negative 2. And if we go a little further and we go to, now what are we talking about, 10 negative, 10 negative, 10 negative? We're talking about meters, okay? So this is all in meters. So think about a meter, and think about taking a meter and saying 0.0000001. Then that's the size of the biggest light wave of light that we can see with our eyes, and we would call it red. So every time you see red, you're actually looking at a wave that's 0.0000001. Okay? Meters. A real tiny wave. When you feel the heat, we can't see heat. We can't see radar. We can't see heat. We can see the impact of heat, right? Something can be glowing white or glowing red. If it's glowing, then what we're seeing is the visible light, the red. But we're not seeing the heat. Somebody said today, well, what about in the summertime when you're playing basketball? You see the waves over the hot concrete, right? Those waves you're not seeing the waves of light. What you're seeing is the air being different densities because it's a different temperature. It turns out that when light travels through different substances, it bends. And if it's more dense, it bends one direction, it bends more than if it, or less, depending on how dense it is. Is that clear to you? So what you're looking at is the density differences of air, of hot air right over really hot surface. That's the waves you see. So you're really not looking at, you can't see infrared, can't see heat. The only things you can see are red, orange, yellow, green, blue, indigo, and violet with your eyes. Is that clear? You can feel heat, obviously. So we feel this infrared. Within that range, we can feel that energy. We can't feel radar waves, and they're really pretty big, 10 to the negative 2, so what does that mean? 0.01 meters, right? So they're pretty big. How big is 0.01 meters? 1/100 of a meter. What is it? A centimeter, right? So a centimeter. So radar waves are actually a centimeter long, about that long. Next is FM. You've heard of FM? 106.5 FM. You've heard of FM?
Yeah.
All right, so FM is actually radio waves, right? So here we're talking about FM radio. Radio waves are, in fact, 1 meter, 1 full meter long. Television waves, I know you watch cable now, but when I was a kid, we'd watch television. Picked up off the air. Waves moving through the air. They're bigger than one meter. Shortwave radios, you've heard of shortwave radios? Never heard of shortwave radios? Well, shortwave radios actually aren't really short when you look at all the electromagnetic spectrum, but shortwave radios are 10 to the 2 or 100 meters long. 10 to the second. Now I guess the reason they call them shortwave radios is because there is a bigger wave, and that's AM. AM is actually 10 to the 4th. Really big waves. Really giant waves. Now, interestingly, you've heard of another kind of wave that I guess most of you have heard of before. Maybe you haven't. It's microwaves. You've heard of microwaves? They're actually how your phone works. And microwave is in between infrared and radio. All right, so somewhere around here, 10 to the 10 to the 10 to the negative 2, somewhere around here, is microwave. Now microwave is what microwave ovens work with, right? They heat up water. Water is very sensitive to microwaves. That's why that's how we cook with them, with the water and the food cooks. That's why things taste a little drier. Why if you put a sandwich in a microwave, you let it heat up a lot, it'll turn real dry and just won't taste as good as if you cooked it over a stove, because the water evaporates. Also, your phone works on microwaves. So imagine the microwave, the same microwaves that cook your food. When you put your phone to your face, those microwaves are leaving the phone and going into your head, as well as the cell tower. However the distance is, it's able to penetrate walls, right? Do you agree? How do you know it can penetrate walls? It has to get the cell tower. And you could be inside, you could be in a room in the office, or in a room in a building, through all this concrete and glass, and that phone is still able to get, that microwaves are able to get from your phone through all this concrete and glass and to the cell phone tower. Do you think it's able to get into your skull?
Yeah.
Sure. Yeah. So those microwave energies, people are afraid that they might cause cancer long term. Something to consider. Using earbuds or Bluetooth devices to call instead of putting the phone up to your head might make sense. Also, keeping your phone in your pockets, near your ovaries and near your testicles, probably not a good idea, right? the sensitive tissues in your genitals and in your brain, probably it's better to keep it further away from those tissues and keep it closer to the tougher tissues, right? The thicker tissues. It may not react as much. Yeah.
Okay, there's a study like the radiation inside our phones to keep your phone like a foot away from you when you go to sleep. Because if you have the phone like directly next to you, you absorb the radiation even if you're not on it.
Yeah, if you're not on the phone, you're sitting there. It's not work. See, it does send a few signals, little pulses of signals, but really it's when you're talking on the phone. You know, because it gets hot, doesn't it?
Yes.
It's getting hot because it's changing electrical energy into microwave energy, and the battery gets hot. That's what's getting hot. All right. The microwave energy is probably safe, but you know what? We thought cigarettes were safe, right? So be careful. That's all I'm saying. And I would not put for various reasons, by the way, especially if you have tight jeans, you put them in your pocket, you're literally bending your phone. It's one of the reasons I think a lot of you end up cracking your screens is because you're putting a lot of stress on that glass and on that metal, right? Yeah. So it's best not to put it in the pants, especially if they're tight and every time you sit down you're stretching it and then relaxing it. All right, enough of that phone business. On the other side of violet is what? What's on the other side of violet? Yeah, ultraviolet, UV. UV light, the stuff that makes you suntan and skin cancer, and people call it black lights. Things are black lights. Black lights are tanning booths. That's gating rings. Yeah, anywhere you see a black light, you turn on a black light, it's black, but it is releasing light. How is that possible? Why do they say that? How is that possible? Anybody? Why do we call it a black light? How is it light and it's releasing? Huh? Black light, UV rays, 10 to the -8, between 10 to -8 and 10, about at 10 to -8. What do we call it? Why do we call it black lights? Even though there's light, it's black. Why?
Because it's just dark. How violent?
Because, guys, what's the only thing we can see? Visible light is the only light we see. All the rest of this stuff is black to us. We don't see it. It's not. If there was no visible light, and we had a room full of UV, radio, shortwave, AM, infrared, all that, we won't see it. There's all these waves are passing right by us right now. We don't see it. We don't feel it. We would feel heat, but that's the only one we'd feel. All the rest of this, we don't interact with it. We don't sense it. It interacts with us, and we interact with it, but we don't sense it. We can't see it. So UV light is ultraviolet. Then after ultraviolet, I know you've heard this one before as well. X-rays. And the last in X-rays are about 10 to -10. So between 10 to -8 and 10 to -10, you have UV, then you have X-rays. And then around 10 to -12, you have gamma rays.
Isn't that the stuff that comes on stars?
That's right.
Out of what?
It's released by nuclear reactions. It comes out of stars. Stars release them. Very good. That's excellent. So that's electromagnetic spectrum. That's the light that's coming from the sun. That's the light that's coming from the sun. Again, this is all being recorded, and you can look at the picture that everybody was having such trouble with and wanted me to produce it. You can see it on the YouTube. So you can also go home and search it, Earth's energy budget. You'll see the same numbers. Resources, being resourceful. All right. So when the light comes in, about 22.9% of all this light comes from the sun, right? About 22.9 gets absorbed by the atmosphere right away. That's good. We want to have some of that heat. If we don't get some of it, we'll turn into a giant frozen popsicle spinning through space. It's absolutely no good. We need some heat here. right? Because space is cold. There's no, you can't, we could not live in space for various reasons, and one of them is it's freezing, below freezing. We cannot survive. We would lose all our heat, yeah.
It's kind of a slow question, but how is space cold if the sun is?
Well, it's not a slow question, it's actually a very good question. The sun, there's not just one sun, there's billions and billions of suns out there.
A whole bunch of stars.
The whole bunch of stars everywhere. But here's the thing, space is big. It's empty and big. The only thing that's in space, but this is the definition of space, right? It's emptiness. And the only thing that's there is this stuff called plasma that comes from the suns, and that's just like little high energy particles, and this electromagnetic energy. As far as we know, it's empty space. And heat, the way you get warmth is you have molecules that are moving. So if there's that few particles in space, that means there's not a lot of particles that are going to give heat, so it's very, very cold. Right? The particles that are there would suck up all your heat. All right. So that's the energy absorbed by the atmosphere really quickly, about 22.9%. And the rest, about 42.6%, is absorbed by the surface. Now there is 23.2 bounces off. You see this reflection? It bounces off clouds and goes off into space. That's because it's short wave. Short wave means it's smaller waves, so anything UV, X-rays, gamma, a lot of that gets bounced off by the clouds. So you go outside on a cloudy day, and you're not going to get a lot of UV light coming through. You're going to get a lot less UV light than you do, but about 23.2% of the light gets bounced off by these clouds. Right now it's happening. The sun is shining the way it always is out in space, and if it wasn't for these clouds, the sky would be blue and the sun would shine brightly, okay? But the clouds are bouncing 23.2% of that light back out into space. This is all natural. All of it's natural. And so the rest of this 47.2 bounces and gets absorbed by the atmosphere, but some of it gets bounced back, about 6% is reflected by this surface. So this is the percentage that's already lost. So we had 100%, we've lost 23 plus 6.7. Somebody want to do the math on that? How much have we lost back to space? Add it up, 23.2 plus 6.7. Okay, plus 11.7?
31.6.
Plus 49.6?
What's the calculator?
Wait, what's the numbers you saying?
Right here, add these numbers together, right here at the top. 23.2, 6.7, 11.7, 49.6, 8.8. Go ahead, add them up. So this equals 100%. So 100% comes in, 100% leaves out. So there's a temperature increase here? So there really shouldn't be any temperature increase, because as much energy comes in, gets processed, gets used, warms us up, whatever, a lot of that heat goes back out. But of course more comes in every day. So it just keeps coming in and leaving. It's dynamic equilibrium. So you have the stable temperature, because as much as comes in, what? Goes out. So that's what's expected. But notice that this heat here, this is radiation, right? So the surface of the Earth absorbed that heat. Now let me ask you something, black lights. Why do we have black lights? What do they do? Yeah.
They detect urine, blood, semen.
Right, they do that. Have you ever seen a movie with people in a club?
Yeah.
Right? Everything, their teeth shine, their eyeballs shine, right? And if they put special paint on their skin, the paint will shine different colors. And that's because that paint, your teeth, your eyes, sometimes your clothes, especially white clothes, what they'll do is they'll absorb the UV radiation, and they will change that waveform, the wave size, the length of the wavelength. They'll re-emit, or they'll release a different kind of radiation that's in the visible spectrum. They'll release red, orange, yellow, green, blue, or indigo, or violet. And so what you see is that yellow light, or that green light, or that blue light. But where did that light come from? It came from the UV getting absorbed by a pigment, then re-emitting that different color that you can actually see. Does that make sense? Yeah.
How do they concentrate the ultraviolet light? We can't see it. Like, they have to have the ultraviolet light to make the UV light.
Well, what they do is that there's certain elements that will release UV energy. They'll make waves that have this length, that are this length. It's just any other energy, like any other light. How does any light bulb work? I could talk about electrons being excited and coming back down to a different orbital, and that releases a certain amount of energy. We could talk about that, but it's not useful right now. Okay? If you'd like to talk about it after class or during advisory, I can explain to you. Einstein actually helped describe some of that. Okay, so the energy gets absorbed at a certain wavelength, and then the surface of the Earth re-emits it, lets it out in a different wavelength, just like the pigment on people that go to clubs, that what happens with black lights, right? Same idea. The Earth's surface absorbs one wavelength and then releases another. And unfortunately, some of that energy gets absorbed by the atmosphere. And of course, clouds then release a certain amount of energy as well. Now, normally, this happens and you have a zero increase in temperature due to this, right? If there's extra solar radiation, then things get hotter. If there's less solar radiation, things might get colder. But as much heat as goes in, it generally goes out, or everybody's happy. So what's the problem? Anybody think of a problem?
They're being absorbed by greenhouse gases.
That's right. Greenhouse gases. What are greenhouse gases going to do?
Make it hotter.
They're going to keep that heat in, right? That's right. They're going to make it hotter because you're going to get a positive feedback loop instead of a negative feedback loop. Right. So let's talk about what happens. It turns out that that most of the gases, most of the energy that's absorbed by greenhouse gases get emitted back to the surface of the planet, rather than being reflected or emitted back out into space. So we got all this heat coming from the sun. Notice most of this is empty space, right? The sun, the hottest part of the sun's here. As soon as you get further away, it dissipates, right? But we get enough energy to warm up the whole planet. That's a good thing. Pluto, poor little Pluto, the poor planetoid that used to be a planet, right? That poor thing's frozen all the time because it's way out there in the solar system. Very little of the sun's energy actually warms it up, because by that time it's really dispersed or been absorbed. So here we have greenhouse gases, and let's talk about what those greenhouse gases are like. These are the greenhouse gases. You need to know them. It will be on the test. You don't need to be able to draw them, but you need to know what they are. Nitrous oxide, water vapor. Yes, water is a greenhouse gas. And isn't that the sad thing? That as you increase temperature, you produce more what? Water vapor. Yeah? The liquid water turns into water gas. And that, in turn, captures more heat, which then does what? Makes more water, makes it warmer, which makes more water vapor, which makes it warmer, that's a positive feedback in this system, and that's no good for keeping homeostasis. So nitrous oxide is another one. Carbon dioxide is the third one. The last is methane. Methane is the byproduct of organic materials being degraded. So when you die, you'll turn into methane. You'll ultimately turn to gas. When you fart, you're farting this, mostly, as bacteria eats your food that's in your intestines. When cows, remember cows being a problem? Do you remember that discussion? Cows, when they eat, especially when they eat corn, but even if they're eating grass, they produce a lot of methane, which is why, and we have a lot more cows than we do humans, right? That's the whole point. We have to have more cows than we have humans, otherwise we wouldn't be able to eat as much meat as we do. Carbon dioxide is produced how? How do you produce carbon dioxide? Yes, that's right. We do breathe out carbon dioxide, that's right. But we do what? What do we humans do? We burn what? Stuff.
Fuel.
Fossil fuels, right? We burn fossil fuels. All right, so methane comes from the breakdown of organic materials. Specifically food, right? Plants and animal matter. And of course water's everywhere on the planet, just about. And let's take a look at where nitrous oxide comes from in a minute. But so that's kind of where we're at. The water vapor is abundant greenhouse gas, it's everywhere. It's normal, we want it to be here. If it wasn't for these gases, we would be a frozen ball of ice. So we need them to keep enough. These gases, our atmosphere, not only gives us oxygen that we need to breathe to live, but also warms up our planet so that we can live on the planet's surface. Carbon dioxide is a small component of the Earth's atmosphere, but it's a very powerful greenhouse gas. Under normal concentrations, it's fine. But we've been increasing it repeatedly. As we increase the CO2 levels, we're increasing the temperature of the atmosphere. Methane. Methane is produced by, look here and make sure you know it. Methane is produced by decomposition of waste in landfills. Specifically, landfills, all right? Agriculture, especially what? Rice cultivation, which means cultivating rice means growing rice. And when they say ruminant digestion, ruminant is the type of digestive system that cows have, all right? So this is from cows, mostly in the United States anyways. And of course, what's the other one that's obvious, that should be obvious to you, I hope, that produces gas? Is poop, manure. Poop is another source of methane. One thing that's not listed here that I believe should be is this idea of the melting of the permafrost. So as the permafrost, which is in Alaska and Canada, melts, it's releasing all the ancient grasses and dead things that have turned into methane. All that methane is being released. And so now methane doesn't have a smell, by the way. The gas itself has no smell. The smell you're smelling in a fart is actually the sulfur, the other gases that are part of the release, the breakdown of the food. Nitrous oxide is a greenhouse gas that we produce when we cultivate soil, when we grow things. Especially when we do use what? Fertilizers, whether they be organic or commercial. If you're using fertilizers, you're going to produce this nitrous oxide. It's a byproduct of growing food. Also, when you burn fossil fuels, that's what combustion means, is burning. When you're burning fossil fuels, and when we make nitric acid. Nitric acid is a very, very, very important part of a lot of different chemical reactions that help you maintain the lifestyle you're used to. So we need nitric acid in various chemical reactions. But obviously the biggest part of the problem here is going to be this use of fertilizers. Chlorofluorocarbons are synthetic, completely synthetic substances. They were actually outlawed for a while. I'm not sure if they still are. They should be. They're heavily regulated, which means that they're outlawed in air conditioners, for instance. And the reasons they're heavily regulated is they also, not only are they a greenhouse gas, they also destroy the ozone. And destruction of the ozone layer is a big problem because the ozone layer is a part of the atmosphere that bounces away that shortwave radiation, that UV light. It helps protect us from being cooked, right? And so we want to make sure that we keep that ozone layer healthy. All right. So I think that's enough for today. It's time for you to go. I hope you learned something, and we'll finish this tomorrow. Remember, we have a lab on Thursday.